right. Continue on with your notes. This is organic set number 2. One thing that I feel that we should talk about before we get into the ways that we represent organic molecules is looking at what some organic compounds are. So we talked about the diamond, pretty easy to remember. Okay, everybody wants one. And another organic compound that you might not be familiar with is gasoline. Okay, so when you go up to the pumps and you basically pump out your gas, this is considered an organic compound. It's organic because it contains carbon and hydrogen. So think about it. We do not want water in our gas tank. Water is polar. And what did we say an organic compound was that you go get at the gas station? That's right, gas. Good. So, water and gas don't mix, just like water and vinegar don't mix. So anything that is nonpolar, and in the case of being an organic liquid, some kind of gas, butane, octane, propane for your gas grills. So just something to be mindful of. Those nonpolar things are things that don't mix with water. And the biggest one that we use is a carbon compound that's made from petroleum products. So let's talk more about ways to represent organic compounds. So this is very synonymous with your skill number 3 in your other packet. Okay. So let's look at the molecular formulas for some of these things. So when we look at the molecular formula, we're talking about how many and what kind of atoms are in the molecule. So let's keep it easy. So let's do ethane. Okay, so C2H6. Okay, so molecular formula is telling you the molecules. Okay, so 2 molecules of carbon, 6 molecules of hydrogen making up the full molecule, which is ethane. Okay. And then we have another way to represent it, and that's the structural formula. So this is going to be a structure. So in doing this, we are now creating a structure. It's the same thing, but again, different way to represent it. Okay. And then there's a last thing, which is a condensed formula. This condensed formula is basically called the empirical formula. Okay. It's empirical because it shows the order of atoms or the molecules. So for example, going along again, same thing, ethane. Okay. I can reduce that, meaning that for every 1 carbon, I would have 3 hydrogen. Now, how did I do that? I did that by basically finding a common factor. A common factor such as 2. So if I divide this by 2, 2 divided by 2 is 1. 6 divided by 2 is 3. So that would be considered a condensed formula, an empirical formula. For every 1 carbon, there's going to be 3 hydrogens. So talking more about organic molecules, we have a comparison here. Okay. We have something called butane. Okay. Butane is something that is found in lighters. Okay. The molecular formula for butane, if you take a look at table O, you'll realize that the prefix for 4 is but. Okay. Butane is going to be in the formula. You would go to, I believe, table P to check these out and ultimately calculate that. Okay. So we have something called butane and something called 2-methylpropane. So let's just do a comparison here. We have a colorless substance that has a melting point of negative 138, and this one pretty close, negative 160. Boiling point of butane is close to 0 degrees Celsius, which is the temperature that water freezes. 2-methylpropane, a little bit lower than that. Solubility in water. Why is this important? this is making you look back at your reference tables and seeing, well, why does this matter? Okay, and we can look at that by looking at the solubility curve, which is found table G. Okay, so it is slightly soluble in water. Really not that much if you take a look at the whole scheme of things. 2-methylpropane, insoluble, so it's not going to dissolve at all. One is highly flammable, the other one is flammable. And if we were to take a look at the molecular formula for butane, okay, it's C4H10. So let's just take a quick look at that. Structurally, if we were to build it, we would have 1, 2, 3, 4 carbons, and then attached, okay, and a hydrogen here, hydrogen here, hydrogen here. And just to keep it a little bit easy for myself, I'm just going to draw these little stick marks, and we can make the assumption that every stick mark is attached to a hydrogen. Okay. So I have 4 carbons, and in total 10 hydrogens. That's my structural formula. So why am I comparing this to something else? I'm comparing it to this because if I were to draw it, let's test ourselves. We have propane, so that's a 1, 2, 3 carbon chain. And at the second carbon, which you'll learn how to do the naming in one of the other videos, is a methyl group. Methyl stands for 1. So I have this structural formula. And if we were to count them all up, okay, we have 1, 2, 3, 4 carbons and 10 hydrogens. So why do I give you this example? I give this to you because we have 2 organic compounds that are similar in a lot of their properties. Very similar. Like flammable, highly flammable, it's still flammable. But they're different in that they have a different structural formula. Okay? So molecular formulas can only tell you so much, but structural formulas can tell you specifically where things are, which can alter some of these properties. So this can go a little bit higher in melting point, or excuse me, a little bit lower in melting point, and this is go a little bit higher in boiling point. And again, it's due to the fact how carbon has arranged itself. Okay. So what we do is we call these guys isomers. Okay. They have basically the same parts, but different arrangement. And we can see that, okay? Same parts. We can see that by the molecular formula. And then a different arrangement if we look at the structural formula. Okay. So why does this matter? It matters that sometimes the more carbons you have, the more power you can get, because the breaking and the reforming of carbon bonds creates or gives off energy. Okay, so if we were to take a look at butane, just to see the percentage of carbons, we would have 4 carbons. Okay, so we have 4 of them. Each of them are 12 grams apiece, roughly. Okay, and the total amount would be 58 grams. So we're getting a percent composition of carbon, and that's going to equal roughly about 83%, which is a lot of carbons, meaning we probably have a lot of energy. And of course we could do the math again, but let's just keep it easy. 100 minus 83 is 17%. So these carbons represent a way in which we can kind of monitor how much power can be released if we alter those bonds. So quick summary here. We have isomers. Okay? Isomers, again, same parts, different arrangements. So they have the same molecular formula, the same percentage composition, right? Because it doesn't matter if I do butane or 2-methylpropane, it's still C4H10. And they also have the same gram formula mass. Doesn't matter how I add it up, it's still going to come up with 58 grams. The key to the differences is that they are structurally different. So the structural formulas are different. And the properties are different. So if you can think about it from, let's say every carbon atom is a Lego. Depending on how I build those Legos will determine whether or not that building or that structure is going to fall down. So wherever you place these Legos, however your structure is formed, will determine whether or not it has a property that's, so let's say, good for making a tower or not good for making a tower. So just something to be mindful of. That's why organic chemistry can be truly mind-boggling, because carbon can really group anywhere it wants. It can move itself, and be in the middle of a carbon chain, or it can be this really, really, really long carbon chain. But one big takeaway is that you have to know that as the number of carbon atoms increases, so do the number of isomers. Okay, so if I have, let's say, 8 yellow Lego pieces, and I can basically put those together in a lot of different ways. Molecularly, you do not have to know how to calculate that, but it would be insane. So quick check of that, which has more isomers? The one that has the larger carbon count.